Okay, let's dive right in. We're going to talk about this invisible energy that powers, well, practically everything we do every single day. It's this incredible force we totally rely on, but you never actually see it. I mean, just think about it for a second. It's in the phone you're holding, the lights above your head, even the car that gets you from A to B. It's this silent, unseen partner in our modern lives, just humming away in the background. So we all know its name, right? Electricity. But what is it, fundamentally? How does flipping a little switch on the wall magically fill a room with light? Well, that's exactly what this explainer is all about. We are going to pull back the curtain on this amazing invisible force. To really get it, we're going to follow a hero on a pretty epic journey. Now, this is a very, very tiny hero, a single particle called the electron. You see, its story is the story of electricity. Okay, so this is the absolute core of it all. At the end of the day, electricity isn't some weird magic. Nope, it's simply the energy we get when electrons start moving. And for them to move, they need a path to travel on, which we call a conductor. Think of the copper wires in your walls. They're great conductors because their electrons are kind of held loosely, which makes them easy to push along. Now, a single electron on its own, it can't really do much. But when you get billions and billions of them moving together all in a coordinated flow, that's when you get something really powerful, an electric current. And we measure how intense that flow is, its rate, in a unit called amperes, or you've probably heard it called amps. But here's the thing. Our little electron hero can't just go on a journey whenever it feels like it. It needs a very specific set of conditions, kind of like the rules of the road. First, you need a power source, like a battery, to give it that initial push. Then you need the conductors, that's the pathway. You also need a load, which is just the thing that uses the energy, like a light bulb. And maybe most important of all, the whole thing has to form a closed, unbroken loop, a complete circuit. If there's a break anywhere, the journey stops. You know, this slide clears up something that honestly confuses a lot of people. In reality, what's actually happening is that our hero, the negatively charged electron, moves from the negative terminal to the positive one. But way back in the day, before we really understood electrons, scientists just kind of guessed and defined current as flowing the other way, from positive to negative. We call that conventional flow, and you still see it in diagrams all the time. Just remember, the electron flow is what's physically happening. So, our electron is on its journey, flowing along in a current. But as it travels, it doesn't just move. It does things. It unleashes its energy in some pretty incredible ways, which, and I love this, we can think of as its four main superpowers. Okay, superpower number 1, heat. As these electrons push their way through a material, they're constantly bumping into atoms, causing them to vibrate like crazy. And all that vibration, that's what we feel as heat. So things with high resistance cause way more collisions, which generates more heat. And that's exactly how your toaster coils get red hot or how an electric iron works. Superpower number 2 is light. So in certain materials, when our electrons bump into atoms, they can actually knock that atom's own electrons into a higher energy state. When that electron inevitably falls back down to its normal spot, it has to release that extra energy, and it does so as a little particle of light, a photon. That right there is the fundamental secret behind every single light bulb and LED. Pretty cool, huh? And superpower number 3? It can actually drive chemical change. The flow of electrons can literally force chemical reactions to happen that wouldn't happen otherwise. When you're charging your phone, what you're really doing is using electricity to reverse a chemical process inside the battery, storing that energy for later. It's like putting the superpower back in the box so you can use it when you need it. And the final, and maybe the most mind-blowing superpower, is magnetism. This is huge. Whenever an electric current flows, it creates an invisible magnetic field all around its path. This is a fundamental link between two of nature's greatest forces, and it's the secret sauce behind every electric motor on the planet, from a tiny fan to a massive industrial generator. So we know what happens when the electron moves, but why does it move in the first place? And what's trying to stop it? Well, it all comes down to two key forces that govern its entire journey. There's a push and there's an opposition. So the push is called electromotive force, or EMF for short. The easiest way to think about it is like electrical pressure. It's what gets the whole flow started. It's the total amount of energy the power source has available to give to each and every electron to get it moving. And we measure this pushing power in volts. And where does this push come from? Well, from sources you see every day. Batteries, they use chemical reactions to create that push. Generators use the power of magnetism to do it. And that power supply brick for your laptop, it's taking the high voltage push from the wall and converting it into the specific lower voltage your device actually needs. All right, now for the opposition. As our electron hero travels, it doesn't just get a free ride. The material it's traveling through creates a kind of electrical friction, something that opposes the flow. We call this resistance, and we measure it in ohms. Every single part of a circuit has at least some resistance. Okay, this table is super helpful because it clarifies a really important distinction. EMF is the total potential energy the battery has. It exists even if the battery is just sitting on a shelf, not connected to anything. Potential difference, on the other hand, is the energy that's actually being used by something, like a light bulb, as the current flows through it. So you could say EMF is the potential to do work, while potential difference is the work actually being done right now. So let's bring this all together. We've followed our hero, the electron, from that initial push of EMF through the pathway of a circuit, unleashing its awesome superpowers, and all while battling resistance along the way. And really, the most incredible part is just the sheer scale of it all. It's not one electron. It is the coordinated journey of trillions upon trillions of them, all flowing in perfect sync that generates the power to light up our cities, to connect the entire globe, and to run the devices that literally shape our reality. It's a microscopic dance of truly epic proportions. And that leaves us with one final thought. We've managed to harness this fundamental force of nature to build the world we live in today. But the journey is not over. As we get better and better at understanding and controlling the flow of these tiny little particles, what comes next? What new worlds will this invisible power allow us to build tomorrow?